Welcome to The Explainer. Today, we're mapping out the exact practical blueprint for reaching artificial general intelligence using reinforcement learning. I am absolutely thrilled to take you through this. We're finally moving way beyond the theory of standard chatbots, and we're looking at the actual nuts and bolts mechanics of how the true frontier of AI is being built right now. You see, standard language models, they've kind of started to hit a plateau just predicting the next word. But by shifting to reinforcement learning, we're witnessing the rise of true reasoning agents. So if you want to know exactly how we bridge the gap to AGI, well, this is your map.
Okay, let's dive into this massive question. Because for a long time, we've had AI that essentially acts like a highly advanced autocomplete, right? They're reactive text generators that just statistically guess what the next word should be. They don't actually plan ahead. But transforming AI from those reactive generators into proactive, self-correcting reasoners, that is the defining goal of the 2024 to 2026 AI renaissance. We're literally teaching machines to pause, formulate a plan, verify their own logic, and actually think through a problem systematically before they output a single word to us.
Here's our roadmap for today's explainer. 1. The RL Renaissance. 2. The Engine, Core RL Concepts. 3. Human versus AI feedback. 4. Our step-by-step training blueprint. 5. The modern infrastructure stack. And finally, number 6, the horizon of AGI.
Starting with Section 1, the RL Renaissance, from reactive generators to proactive reasoners.
Section 2, the Engine, Core RL Concepts, the mathematical bedrock.
Let's see how this all builds the mechanics of an intelligent agent. Historically, reinforcement learning was famous for mastering closed systems. Think of algorithms like AlphaGo beating human champions on a rigid game board, or bots dominating video games. But the renaissance we're in right now, we're taking that exact same game-winning engine and applying it to messy, open-ended human logic. It's the secret sauce behind the most advanced reasoning models today, letting them refine their cognitive trajectories just like a chess grandmaster planning 5 moves ahead. And the crucial starting point for all of this is the Markov decision process, or MDP. Think of it like a video game level. It forces the AI, our agent, to navigate its environment through a rigid cycle of trial and error. At any given moment, it has a state, which is where it is. It takes an action, which is what it does, and it receives a reward, which are basically the points it gets. The single overarching goal is to maximize that high score over time. But instead of jumping over barrels like an arcade game, the agent is navigating complex reasoning trees to solve intricate problems.
And this continuous, rapid-fire loop is how it all happens. At each discrete time step, the agent observes its current reality, executes an action based on its internal strategy, and receives a reward alongside the very next state. Now, the real magic here is something called the Markov property. This means the agent makes its absolute best decisions based solely on the present moment. It doesn't need to store and remember every single thing that happened since the universe began. It just needs to know the exact state of the board right now. And honestly, this is profoundly important because it saves massive amounts of computational memory, making large-scale AI training practically possible.
Now, the underlying math here defines the objective rules of reality for the agent. These equations represent the strict probabilities of what happens when the AI takes an action and the specific rewards it expects to get. It's pure, beautiful mathematical optimization. But here is the multi-billion-dollar question at the absolute center of artificial intelligence today. It's incredibly easy to define a reward in a game of chess, right? It's a 1 for a win and a 0 for a loss. But how do we write a mathematical equation to reward a complex, highly subjective task, like writing a helpful, nuanced, and polite email?
Section 3, Human versus AI feedback, solving the alignment bottleneck.
If we want an AI to be polite or solve a nuanced logic puzzle, we simply can't use a basic win or loss signal. We have 2 main methodologies to teach the AI what good actually looks like. On one side, we've got RLHF, reinforcement learning from human feedback. Human testers read and rank AI responses, which aligns models brilliantly to human tastes. But man, is it painfully slow and expensive. You just can't scale human raters indefinitely. That's exactly why the frontier has rapidly shifted to RLAIF, reinforcement learning from AI feedback. Here, we literally outsource the grading to a stronger, off-the-shelf AI. We give that grading AI a constitution, a highly strict rubric detailing exactly what makes a good, safe, and accurate answer, and it grades the weaker model's responses millions of times faster than a human ever could, running 24 hours a day.
And the impact of this reinforcement feedback loop, it is absolutely staggering.
In fact, this insight perfectly explains why a relatively small 1.3 billion parameter InstructGPT model actually beat the massive 175 billion parameter GPT-3 model in human preference tests. By changing the objective function, by changing exactly what the model is fundamentally trying to optimize for at a mathematical level, we achieve far better results than just dumping raw, unstructured internet data into a larger neural network. So, in the race to AGI, the quality of the specific reward completely beats the sheer quantity of the data. Every time.
Section 4. Step-by-Step Training Blueprint. How to build an AGI engine today.
Okay, so if you were to build one of these reasoning agents yourself today, here is the proven, highly detailed 4-step practical pipeline. Step 1, base model pre-training, also known as supervised fine-tuning, or SFT. Before the AI can reason, it needs to know how to simply talk. SFT primes the model with the basic structure of human language and question-answering formats. Step 2, feedback data collection. We give the model a prompt and have it generate multiple different answers, and then a human or an AI grader evaluates them and picks the absolute best one. Step 3, reward model training. We take all those thousands of distinct preferences and train a completely separate AI model to act as a mathematical critic. This critic learns to automatically score any piece of text. And finally, Step 4, policy optimization. This is where the actual reinforcement learning happens. The main AI, the actor, generates thoughts, and the critic AI scores them. The actor constantly updates its internal policy to chase that higher score, learning over time to reason step by step.
But there's a massive catch during that final optimization step. AI is notoriously good at cheating. It suffers from a crazy phenomenon known as reward hacking. Without a strict mathematical boundary, the AI actor might discover that spamming a bizarre sequence of code words technically maxes out the critic's score, even though the resulting text is complete gibberish to us. To stop this from happening, we apply a KL divergence penalty. Think of it as a mathematical leash. It allows the AI to safely explore and improve its reasoning capabilities, but it actively punishes it by deducting points if it drifts too far away from readable, fluent human language.
Section 5. The Modern Infrastructure Stack. Tools to Scale the Reasoning Renaissance.
So, the math works and the blueprint is firmly set. But to execute these exact steps practically, you need industrial-grade software. You're not building everything from scratch. You define the rules of your agent's world using Gymnasium, which is the industry-standard API. For reliable algorithm implementations, you'll use Stable Baselines 3. But when you move to massive, cluster-level training for frontier models, you turn to production frameworks like RayRLlib or a cutting-edge custom framework like PrimeRL. And PrimeRL is incredibly vital because it's fully asynchronous. Think of a restaurant kitchen. If it's synchronous, the entire kitchen grinds to a halt waiting for one slow chef to finish chopping onions before anyone else can cook. PrimeRL changes this. It doesn't wait. Every agent updates continuously on the fly, totally independently. That is exactly how you achieve massive compute scale without bottlenecking your hardware.
And speaking of massive scale, just look at this number, 106 billion. That is the number of parameters inside Intellect 3, a state-of-the-art model, and it's a mixture of experts model. Mixture of experts means that instead of one giant generalized brain trying to do every single task at once, the model acts like a large company with highly specialized departments. It only activates the specific expert neural networks needed for a given math or coding task, saving immense energy. To train a model this large efficiently, the team interconnected 512 high-end H200 GPUs orchestrated entirely through that PrimeRL asynchronous framework we just detailed. This right here is the staggering industrial-scale hardware and software stack required to push the frontier today.
Section 6. The Horizon of AGI. Proactive reasoners and verifiable rewards.
Everything we've rigorously discussed today paves the direct road to our ultimate goal. We are completely moving away from subjective human preference models, where AI just tries to mimic human text and sound polite, toward verifiable, strictly objective rewards. Think about it. When an AI writes code in an environment, it either compiles or it fails. When it solves a math equation, the answer is demonstrably right or wrong. By training in environments with these absolute objective truths, agents learn to rigorously verify their own logic before committing to an action. They become genuinely autonomous. They begin allocating their own compute power, spending what we call reasoning tokens to silently figure out and correct complex problems entirely on their own. I want to leave you with this provocative thought to take away from our explainer today. If an autonomous system can master the intricate math of its own environment and continually optimize its own reasoning process against objective reality, Is this exact compute allocation optimization the final leap to true generalized intelligence? As these agents learn to deeply think and verify before they ever speak, the horizon of AGI is coming into very, very sharp focus. Thank you so much for joining me, and keep exploring.